Hello again. This is Math 2232 coming to you from the College of DuPage. And this is part 2 of the video lecture for 1118, Applications of Parametric Representations of Arc-Length Differential and more. Now, as you recall, we concluded the last video by realizing that we now had a third representation, this time with respect to dt, of the arc length differential. Previously we had ones with respect to dx and with respect to dy. Now we have dt. And previously we also used ds to represent surface areas of revolutions, and we're going to do that again. But previously we did it with respect to x and y, and now we're going to be doing it with respect to dt. And so here are the formulas. Then. So if a smooth curve C is given by x equal f of t and y equal g of t, and it does not cross itself on the interval where t ranges from a to b, then the surface area of the revolution formed by revolving C, the curve, around a coordinate axis, and we could also talk about generalized rounding it around other axes, but let's just talk about the coordinate axis here, is given by one of the following. So if we're revolving around the x-axis, and that means that g of t is bigger than or equal to 0, or for g of t bigger than or equal to 0, then we have s is equal to 2 pi, the same multiplier we had before, but now we're integrating g of t times what we have ds, and so this is going to be the square root of dx dt whole squared plus dy dt whole squared dt. And similarly, if we're going around the y-axis for f of t greater than or equal to 0, the surface area of revolution then is going to be 2 pi, the integral from a to b, f of t, and then this is ds again, but now it's in parametric form. So this is dx dt whole squared plus dy dt whole squared dt. Now, these formulas may be easier to remember if you just think about this as being ds, and then the formulas can be written. Formula 1 can be s is equal to 2 pi, the integral of g of t, ds. And here, s is 2 pi, the integral of f of t, ds. And again, s is going to be parameterized this way often in your Calculus 3 studies. So let's apply that with a couple of examples. So here we're going to let C be the arc of the circle, and this is x squared plus y squared, running from 3, 0 to 3 halves, 3 over 2 times the square root of 3. So you see this is the curve C. We're going from there. It's a circle of radius 3, and we're going from, this is the arc of the circle. But then we're revolving C about the x-axis, so we're revolving this around, and so we want to find the surface area of this spherical dome that we have here. Now again, for maximum learning, you should pause the video here and give this problem a try. If you solve it, congratulations. If not, you're better prepared to understand the solution. I am going to point to a symbol like this later, but I'm not going to repeat the words. Okay, so please give it a go. Let's see how you. Okay, well, you're representing C, and you do have to represent C parametrically by the equations x is equal to 3 cosine t and y is equal to 3 sine t. Now you can ensure that that is happening because you're starting here and going up to there. You see when t is equal to 0, you're at 3, 0, and then you go up to here. Whenever you end up at, this is going to be, you're going up to t equal pi over 3, and you're solving that when x is equal to 3 over 2. Now, on this interval, C is smooth, y is non-negative, and so you can apply the theorem that we just talked about to obtain a surface area. And so this s is going to be the integral of 2 pi. This is the integral from 0 to pi over 3, and then you use y, so there's 3 sine t, and this is your surface area differential. arc length differential. And so it's going to be minus 3 sine of t whole squared plus 3 cosine t whole squared. Now this is going to simplify very nicely when you do that, because there's going to be a 9 and you'll have sine squared cosine squared. And so you're going to simply be integrating. The 3 comes out, and that makes this 6. And then what you're going to do is this 3 comes out, makes it 6. We have another 3 that comes from the square root, and so eventually it's going to be 18. But you're integrating from 0 to pi over 3 sine, which is going to give you the minus cosine, and then you'll plug in the numbers. And when you're plugging in these numbers and using the fundamental theorem of calculus, you will get that this is going to be minus 18 pi times 1/2 minus 1. So this is going to be minus 1/2, and that together is going to give you 9 pi. Okay, so please make sure you understand this problem. Let's do another problem with the surface area. And so here we're finding the surface area generated by revolving the curve given about each of the given axes. So we're doing it about the x-axis and we're doing about the y-axis. Okay, so here we have x is equal to 2t and y is equal to 3t. And if you think about this for a while, eliminating the parameter, you know, these are just lines, but t is running from 0 to 3. So please give it a go. Let's see. Okay, well, dx dt is going to be 2, dy dt is going to be 3. We plug that in, and we're integrating this as y. In this case, it is x in the other case. So on a, you're really integrating, that's the square root of 13. We pull it through. We're integrating t. We add 1 to the exponent, divide by the new exponent. We plug the numbers 3 and 0 in, and we get this is 6 square root of 13 pi times 9 over 2, which will simplify to 27 square root of 13 times pi. Similarly, down here, you're using the x. You still have the square root of 13. So when you integrate t, you get t squared over 2. You plug in the endpoints using the fundamental theorem of calculus, and you get this as 4 times the square root of 13 pi, 9 over 2, and that's going to be 18, the square root of 13 times pi. Okay, looking ahead then, back to the calendar, we are finished. You watched the video today, and hopefully you benefited from it. Do make sure you understand this, because this is definitely something that I consider covered in the lecture. Looking ahead to next week, we will have, and looking ahead further again, we have a short time left. Much to do, but it fits. It'll work out just fine. And we're going to start with polar coordinates on Monday during this short week. So a most important lecture then. Again, we'll only have class one day next week, but you can do math every day, and I will be doing math every day. So I have one short week and then 2 more, so a total of 3, but one of them is very short. And that concludes with our final exam testing window. Still time to catch up. And it is important because the final exam counts for, at a minimum, 1/3 of your grade, and given the upside opportunity, it can count for much more. So we're still covering new material, so you know, you want to be reviewing as well as engaging rigorously as we go forward. After all, this is a 5-hour course. It counts a lot for your GPA. It's also the gateway course for Calc 3. So please engage rigorously, and I wish you great success. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. Strive to make a difference. Look forward to seeing you guys Monday in class. And take care. God bless.